Hello everyone, welcome to my channel. My name is Adam and I'm from Morocco. This is part 2 of a two-part video series where I demonstrated the solution to a tough mathematics exercise from an Olympiad. I have linked to part 1, which will be uploaded at the same time as this video, in the description, so check it out. Today I'm going to continue demonstrating my solution right to the end, so let's get going. Last time we left off trying to calculate the difference between these two sums, and through a series of steps we've been able to simplify it to this formula. And today we are going to start from here. To do that, let me take a look back at the shape we drew in the last paper. So if you take a look again, lengths CH1 and AH1 add up to AC. So do lengths CH2 and AH2, and so on up to CH 2017 and AH 2017. Therefore, we can substitute back in our series as follows. We write the common factor AC, open the parentheses, and instead of CH1 we write AC minus AH1, because AH1 plus CH1 equals AC. Therefore CH1 is equal to AC minus AH1 minus AH1, the original one. And we do the same for all of the other terms. So CH2 minus AH2 becomes AC minus AH2 minus AH2, and we keep doing the same all the way up to the last term, which is AC minus AH 2017 minus AH 2017. And let's close the large brackets. The next step is to combine all of these ACs that we get from every one of these terms, and to do that we need to count the number of terms. So we have one term, two terms, and so on, and here is term number 2017. Notice that the index here of 8 tells us the number of terms. This is the first term, this is the second term, this is the 2017th term. So overall, there are 2017 copies of AC. So we write AC as a common factor, open big parentheses, and we write 2017 times AC, because we've got 2017 copies of AC, minus, and we combine each of these terms and factor to 2. That's minus 2 lots of AH1 plus AH2 plus all the way up to AH 2017. Close the little brackets and close the large brackets. Now let us expand the large brackets once again. So what have we got? We've got AC times 2017 AC, which gives us 2017 AC squared, minus 2 times AC times the sum inside of the little bracket. That is AH1 plus AH2 plus etc. all the way up to AH 2017. So what we've been able to do so far is to rewrite this difference of two really long sums into an expression that only involves one sum, which is this sum of AH's. And so the next natural step would be to try and compute this sum. So let us try to do that. Let us try to compute what AH1 plus AH2 plus AH3, etc., all the way up to AH 2017 really equal. To evaluate this sum, we are going to use another theorem of elementary algebra, and that is Felices' theorem. So what is Felices' theorem? Well, Felices' theorem says that if we have got two parallel lines, or one version of it at least, so we've got two parallel lines and two lines that cross these two parallel lines, each at 2 points. So let me label some of these points. Let's label this point A, this point B, this point B prime, this point C, this point C prime. Then Thales' theorem says, of course, under the condition that line BC is parallel to line B prime C prime, we've got a ratio of distances, which is the following: AB over AB prime is equal to AC over AC prime, which equals BC over B prime C prime. So you start from the intersection point and you go AB over AB prime is equal to AC over AC prime, which is equal to BC over B prime C prime. Let us therefore apply this theorem to our problem. If we go back to our shape one last time, we see that we could use Thales' theorem several times. For example, consider line segments BC and D1H1. Both of these lines are perpendicular to line AC, therefore they are parallel. And if we use point A, which belongs to the line H1C and D1B, we could use a Thales' theorem. So let's write down these conditions. We said that line D1H1 was parallel to line BC, and we said that point A belongs to both CH1 and line BD1. I'm just repeating what I just said. Therefore, we could use Thales' theorem to conclude that AH1 over AC is equal to AD1 over AB. For the moment, I'm not going to need this third part of the equation. I'm just going to focus on these two. So now, how much does this ratio equal? Well, remember that way at the beginning of the exercise, we divided line segment AB into 2018 equally length segments. Therefore, each segment would equal 1/18 of the total segment AB, which includes AD1. Therefore, AD1 over AB is equal to 1 over 2018. So let's write that down here. This equals 1 over 2018. Therefore, we could deduce that AH1 over AC is equal to 1 over 2018. And to deduce AH1, we multiply both sides by AC, and we get that AH1 is equal to AC over 2018. Now, if we repeat the same process with, for example, line D2H2 and line BC, following the same conditions as last time, we could use Thales' theorem to induce that AH2 over AC is equal to AD2 over AB. Hopefully you could see why. So let us write that down. So AH2 over AC is equal to AD2 over AB. And how much does this ratio equal? Like last time, since every one of these 2018 segments is of the same length, and AD2 is made up of two of these segments, therefore it's going to be 2018ths of the length of AB. Again, since AD2 is equal to AD1 plus D1 D2, and these two lengths are both equal, and each is 1/2018th of line segment AB, we can deduce that AD2 is 2/2018ths of AB. So let us write that down. And like last time, we could deduce that AH2 over AC is equal to 2 over 2080. Therefore, AH2 is equal to 2 times AC over 2018. Through similar reasoning, we could go on using Felices' theorem all the way up to the last index that we have. And if you notice a pattern here, AH1 is equal to 1 times AC divided by 2018. AH2 is equal to 2 times AC divided by 2018. And in fact, this pattern keeps on forever. And you could use Thales' theorem to easily prove that. So all the way up to AH 2017, which would be 2017 times AC divided by 2018. Right, so if we go back to the difference we wanted to calculate at the beginning, we could now use these formulae that we got thanks to Thales' theorem, the formula I boxed in red, to express the difference in other terms. So if we just write the difference again, we can substitute our formulae that we got into this sum. So we will have 2017 AC squared minus 2AC lots of. Instead of AH1, we could write AC over 2018. Instead of AH2, we could write 2 times AC over 2018, and the pattern keeps all the way to AH 2017, which is equal to 2017 AC over 2018. We close the brackets, and now we have a common factor inside of the brackets, which is this fraction AC over 2018, which would be a common factor in all terms, and therefore we could factorize it. So if we factorize it, we have 2017 AC squared minus 2AC times the common factor AC over 2018 times what is left in this first term when we take away AC over 2018? Well, just 1. What about this second term? If we factor out AC over 2018, what's left is this number, 2. And the next number, of course, would be 3. And so on, all the way up to 2017. So, we can rewrite what we got. So, as 2017 AC squared minus 2 times AC times AC is AC squared over 2018 times the sum of the integers from 1 up to 2017. The last bit of mathematics I'm going to use to solve this problem is a well-known formula which says that the sum other integers all the way up to a given integer n, so 1 plus 2 plus 3 plus 4 all the way up to n is equal to n times n plus 1 over 2. This is a really interesting formula which I may prove one day, but today we're just going to take it for granted and we are going to use it to evaluate this sum we have inside of the bracket. So now our difference becomes 2017 AC squared minus 2AC squared over 2018 times. This is the sum of integers up to 2017. So n in this case is 2017. So by this formula, we know that the sum of integers up to 2017, which is what we have inside of the bracket, is 2017 times 2017 plus 1, which is 2018, divided by 2. So let's write that down. So it's 2017 times 2018 divided by 2. And now the magic comes along. We can actually simplify this fraction. The 2 on the numerator and the 2 in the denominator cancel out. And the 2018 here in the numerator with this 2018 in the denominator also cancel out. So what we've got left is 2017 AC squared to the first term minus what's left here is AC squared times 2017, which we can rewrite as 2017 AC squared, and surprise, these two terms also cancel out and we've got 0. So after all of this work, we've been able to show that the difference of these two sums equals 0. Therefore, they are equal. And let's just write this down. So that's CD1 squared plus CD2 squared plus all the way up to CD 2017 squared. This is equal to AD1 squared plus AD2 squared plus all the way up to AD 2017 squared. So the two sums are equal. And let us call this equation equation number 2. Right, so now after all of this effort, we've been able to show that these two sums are equal. And if we take this equation 2 and add it to equation 1, which was just Pythagoras' theorem once, if we add these two equations together, we are going to get the equation that we were asked to show in the exercise. So let me just write that. Just turn the page and write that. So by adding equations number 1 and number 2, we finally get the result that we wanted to show right from the beginning, that was asked from us, which is that CD0 squared plus CD1 squared plus CD2 squared all the way up to CD 2017 squared plus CD 2018 squared is equal to AD1 squared plus AD2 squared plus all the way up to AD 2018 squared. So with that, we're done and we could finally write QED. And with that, we conclude our solution to this incredibly fascinating mathematical problem. Thank you so much for watching. If you enjoyed the video, please give it a like, share it, subscribe if you like to see more content on this channel, and leave a comment if you have any suggestion or any question about any part of this demonstration, please do not forget to subscribe to the main channel, Moroccan Geographer. The link is in the description. Make sure you also watch part 1 of this two-part series of videos. And until next time, see ya!